For the beam shown below with constant E 200 gigapascals by double integration method, determine the slopes just to the left and just to the right and deflection at B. So before I proceed, let me remind you that for those who are my subscribers, please don't be selfish in sharing my videos to your friends and to your friends' friends. And for those who are new, please subscribe and you will not waste your time in visiting my channel. And if you subscribe, because I plan to make this your one-stop channel. You know, it's very tiring to create videos, especially the drawings, and I strive hard to make the presentation detailed with more details so that you can understand. And that's the remaining inspiration that I have when you share my videos to your friends and to others. So don't be selfish, because I'm not wasting my time to share all I have, because that's my plan, that's my legacy, to present and share my potential, my talent to future engineers. I hope that you will become future engineers and you will be good engineers too. So first, let's consider BCD. We sum up moment about B equals 0. So we have R sub C times 4 equal minus 30 times 6. So R sub C is equal to 45 kilonewtons. So let's put it there. So considering BCD summation versus Y, so therefore just to the right of B, the internal reaction should be 15 downwards as shown. Then just to the left, by action reaction, it's also 15. So considering now AB, summation versus Y equals 0, or RY equals 0, so we have AY plus 15 minus 36 times 6. So that's why AY is equal to 201 kilonewtons. So let's show it there. Then let's assume that moment is positive, so it is clockwise. So moment is 0 equals MA clockwise plus 36 times 6 times 3, then minus 15 times 6. So MA is equal to negative 558 kilonewton meter. So let's put it there. That's negative 558 kilonewton meter. We now establish our differential equation for portion AB. So EI AB y double prime AB is equal to, or EI, the value is 200 times 10 to the 6 kilopascals, 200 gigapascals, so 200 times 10 to the 6 kilopascals times 800 times 10 to the 6 mm to the 4th divided by 1000 to the 4th to make it kilonewton. To make this meter to the 4th, so kilonewton per meter square times meter to the 4th, so 160,000 kilonewton meters square. Therefore, so that's it. And EI of BCD is only 0.75 of EIAB. So let's now establish the differential equation for portion AB. So we have EI y double prime AB is equal to 201 times x minus 558, then minus 18 times x over 2, sorry, 36 times x over 2, so minus 18x squared. Integrating once, EIY prime AB is equal to 100.5 x squared minus 558x minus 6x cubed. There's no c sub 1 because the slope and deflection at A for fixed support are zeros. The slope and deflection are zeros. So c sub 1 is 0, c sub 2 is also 0. Then integrating again, EIY-AB is equal to 33.5, so 100.5 divided by 3 is 33.5 x cubed minus 279 x squared, 558 over 2. Then 6 over 4 is 1.5, so minus 1.5x to the fourth. Then we can now set x is 6. We can compute theta at b just to the left in this equation here, because there are no constants. So AI theta b left is 100.5 times 6 square minus 558 times 6, then minus 6 times 6 cube. So therefore, theta b just to the left is negative 1026 over EI, then divided by 160,000. So theta b just to the left is equal to negative 6.4125 times 10 to the negative 3 radians. Then we can also compute the deflection at B by setting the value of x into this equation 6. So EI delta B is equal to 33.5 times 6 cubed minus 279 times 6 squared minus 1.5 of 6 to the fourth. So delta B is equal to negative 4752 over EI. So the shortcut to computing deflection in mm is, instead of 160,000, we just divide that by 160. And the unit would now be in millimeters. So delta B is equal to negative 29.7 mm. Then let's establish the differential equation for portion BCD. Remember, the moment of inertia is just 0.75 of the moment of inertia here. So let's have this section, and this is our origin, which is at B. There's no problem because we know already the deflection at B. And because this is the origin, the constant C sub 3 would be the slope just to the right, and C sub 4 is the deflection at B. So the equation is EI, E times 0.75I, Y double prime BD is equal to negative 15 times x plus 45 times x minus 4. Divide everything by 0.75, EI, Y double prime BD is equal to negative 20x plus 60 quantity x minus 4. Integrating once, EIY prime BD is equal to negative 10x squared plus 30 quantity x minus 4 square plus C sub 3. Integrating again, EIYBD is equal to negative 10 thirds x cubed plus 10 quantity x minus 4 cubed plus C sub 3x plus C sub 4. And when x is 0, then YBD is equal to the deflection at B, which is already computed, negative 4752 over EI when x is 0. So that means C sub 4 is negative 4752. So EI times negative 4752 over EI when x is 0. Remember, the deflection at B is negative 4752 over EI, then equals C sub 4, because everything here will be 0 or ignored, especially this. So C sub 4 is negative 4752. Then, having known C sub 4, we can solve C sub 3, because when x is 4 at C, the deflection in portion BD is 0 also. So 0 equals negative 10 thirds of 4 cubed. This is 0, so plus C sub 3 times 4 plus C sub 4, which is negative 4752. Computing for C sub 3, C sub 3 is equal to 3724 over 3. Remember, C sub 3 divided by EI is when x is 0. When x is 0, these first two terms, first term is 0, the second term is ignored, and we also have C sub 3 left. Since this is the slope, then that's the slope at B just to the right. Therefore, theta B right is equal to 3724 over 3 EI then divided by 160,000. Theta B right is 3724 over 3 over 160,000. So theta B right can now be computed, and that completes our solution. So 7.758 times 10 to the negative 3 radians.